All right, today we're doing something a little crazy. We're going to take on a giant. We're launching an assault on what might be the most unbreakable, most profound, and, let's be honest, most frustrating theorem in all of mathematics. Yep, we're going after Kurt Gödel's Fortress of Logic. So let's get into it. Okay, so this is it. This is our target, stated in all its glory. Now, what does this actually mean? Well, put simply, Gödel proved that for any logical system, one that's strong enough to do basic math, there will always be statements that are true, but that you can never, ever prove are true using that system's own rules. It's like this permanent, I know this is true, but I can't prove it, that's just baked into the very fabric of logic. So this gets to the core of the problem. You see, for any system of math, there's kind of this ultimate wish list of 3 things you want. First, you want it to be consistent, so it doesn't contradict itself. You also want it to be powerful enough to actually be useful. And finally, you want it to be complete, which means it can answer any question you throw at it. Seems totally reasonable, right? Yeah, well, wrong. Gödel just walks onto the scene and proves that this perfect little trio, it's impossible. You can have any 2 you want, but you can never, ever have all 3. And that right there, that's the fortress wall we're about to charge. Look, a direct attack, it's just not gonna work. Pretty much every mainstream logician agrees the proof is rock solid. So we've got to think outside the box here. This is our plan of attack, a 4-pronged assault to subvert, escape, or maybe even just redefine the rules of the game. All right, assault number 1. This is our anarchist gambit. The strategy here is pure rebellion. Gödel's theorem literally starts with the words, any consistent formal system. So, what if we just aren't? What if we decide to tolerate a little bit of chaos? So, in classical logic, the kind Gödel was working with, a single contradiction is like a logical atom bomb. Seriously, if you can prove that something is both true and not true at the same time, the whole system just collapses into useless nonsense. But paraconsistent logic? It's totally different. It says, hey, you can have a little paradox over here in some weird corner, and we'll just quarantine it. The rest of the system can keep on working just fine. Okay, so here's the gambit. We build our own system, let's call it Math Plus, using these new rules. Then, when we run into Gödel's super tricky sentence, the one that basically says, I cannot be proven, we don't panic. We just go ahead and prove that it's both true and false. We embrace the contradiction. And because that paradox is contained, the rest of our system is totally fine. And guess what? In a way, it's complete. So, the big question. Did we do it? Did the anarchists actually manage to tear down that wall and get to a complete system? Well, kinda, yeah, but with a huge catch. See, this isn't really a disproof. It's more like a radical redefinition of what truth even means. We've built a system that's complete, sure, but we had to accept that some things can be both true and false at the same time. It's a philosophical victory, I guess, but it's one that most mathematicians just aren't willing to live with. Okay, assault number 2. This time, we'll leave consistency alone. Instead, we're going to attack the system's power. And specifically, we're going right after the idea of infinity. You see, Gödel's theorem relies on a system that can handle all the natural numbers. 1, 2, 3, on and on forever. An infinite set. But the ultra-finitist comes along and asks a really simple but profound question. What if infinity is just a fantasy? What if the only numbers that truly exist are the ones we can somehow physically represent in our universe? Maybe there's a biggest possible number. Maybe it's a googol, or maybe it's the total number of particles in the universe. In this view, any number bigger than that cosmic speed limit, well, it isn't a number at all. It's just meaningless scribbles on a page. And this is where you see the trade-off. In a totally finite system, Gödel's tricky sentence might not even be possible to write down. And since the whole system is finite, you could, in theory, just check every single statement one by one. So it's complete. But what's the catch? Well, we've achieved this victory by completely gutting our mathematical universe. We had to throw out the incredibly powerful idea of infinity, which is the absolute bedrock of stuff like calculus. Okay, so our first 2 assaults were pretty radical, right? But this next one, this is on a whole other level. We're about to attack the very definition of proof itself by diving headfirst into the bizarre world of quantum mechanics. So this approach just throws binary logic, true or false, right out the window. Gödel's whole proof assumes a statement is either 100% true or 100% false. But what if, in the quantum world, a statement could exist in a superposition? Like, it's 70% true and 30% false at the same time. In a system like this, a proof isn't just a series of logical steps. It's an actual physical process that ends up as a probability. So in this quantum world, Gödel's sentence isn't a paradox anymore. It would just settle into a stable superposition, never being fully true or fully false. We've escaped incompleteness. But the catch, and there's always a catch, is that we've changed the rules of the game so much that you have to ask, are we even doing math anymore? We basically dodged a digital problem by just embracing analog uncertainty. All right, for our final assault, we're putting down the mathematical tools and picking up a philosophical argument. This strategy doesn't even try to break the theorem. It tries to just step right over it by claiming it doesn't apply to us, to humans. This gets to the core of what's called the Lucas-Penrose argument. It basically says, yeah, Gödel's theorem is a perfect description of the limits of machines, of formal systems. But the human mind? Oh, that's something else entirely. Just think about it for a second. Gödel shows us how to build this sentence G that a system can't prove. The system is completely trapped by its own rules. But we, as human mathematicians, we can stand outside that system, look at G, and immediately see that, yeah, it's true. Our minds can make this intuitive leap that the machine just can't. So when you get right down to it, this isn't a disproof at all. It's a reframing. The theorem about the limits of formal systems, it's still standing, completely untouched. This argument simply makes the really bold claim that we are not formal systems, that human consciousness and intuition operate on a whole different level. So, after 4 pretty daring assaults from 4 totally different directions, the fortress of Gödel's theorem is still standing. But that doesn't mean our mission was a failure, not at all. In fact, trying to find a way around these walls has shown us just how deep their foundations really go. I mean, each of these attempts taught us something really profound. The anarchists, they showed us that absolute consistency is a choice, not a law of the universe. The pragmatists, they revealed that our very belief in infinity is what guarantees incompleteness in the first place. The mystics, they suggested that maybe our simple true-false logic is just too crude of a tool to capture reality. And the philosophers, they argued that the human spirit will always try to be one step ahead of any machine it creates. And this kind of brings us to our final thought here. Maybe the whole quest to disprove Gödel was never really about finding a flaw in his logic. Maybe it was about discovering just how radically we have to change our own assumptions about truth, about reality, about ourselves, to even begin to escape its conclusions. Maybe the goal isn't to break the rules of the game, but to realize that we have the power to play an entirely different one.